Okay, welcome friends to the second part of the homeostasis podcast. In the last podcast we talked about the necessity of organisms keeping internal conditions constant in a very narrow range of suitable internal conditions that are hospitable to the molecules that we have in our bodies that we depend on to do all the things they do to keep us alive. We're going to continue with that. The first example we talked about was body temperature. There are many, many, many examples we could use. I want to talk about one other, and it's pH. Gives us a little chemistry review, and we will refer to it like with temperature throughout, off and on throughout the course. So it's a kind of a small recurring theme. So without further delay, another example of homeostasis is maintaining a constant pH. And before we go even a step further, we need to remember what pH is. So let's do a little time travel in your minds back to, I bet even middle school, maybe before then, where you all might have talked about what pH means. pH is simply a measure of how many hydrogen ions there are in a solution versus hydroxide ions. So it's a measure of how many very reactive little ions there are. So let's remember a little bit about water. Okay, because that's what the bottom line is for pH is water. We need to understand that. In any glass of water, there are obviously lots of H2O water molecules. That's what water is all about. It's H2O, two hydrogens, oxygen bound with an oxygen together, covalent bonds, very strong, it's stable. It is a very plentiful molecule. Now, in any given glass of water, a few of these molecules, for whatever reason, disassociate. They will fall apart into ions, okay? Two ions. One of those ions is a hydrogen ion, written as H+. The other is a hydroxide ion, written as OH-. If you can see, if you put those two together, you'd have two H's and an O, and again, you'd have your very neutral, happy little water molecule back. But when it is disassociated like that, the hydrogen ions and the hydroxides are both very, very reactive. So let's talk a little bit about these hydrogen and hydroxide ions. Extremely reactive, extremely eager to engage in chemical reactions with other molecules. Now, in a glass of pure water, this is essentially inconsequential, meaning it just doesn't matter very much. The reason it does not matter is that very few of the water molecules at any given point in time have disassociated, so there's just not very many of them. Secondly, when they do disassociate, they equal out. There's an H+ for every OH-. We have neutral charge. They equal out. So, giving us a pH of 7. If you will recall, we've got over here on the right side of the page that pH scale, the 7 in the blue being neutral. If you go up on the scale, meaning towards this bright red at the top of the screen, you go all the way down to 0, which is the strongest acid. Okay, the strongest acid. I believe they have battery acid listed. At pH 3, I believe there's cola and orange juice. And then the other extreme, on the other side of 7, down on the lower part, you will go up to 14, which is drain cleaner, I think. Yeah, liquid drain cleaner. Ammonia is at 11. So some really caustic substances in there. So, that's our pH scale, 0 to 14, 7 being neutral. And in a pure glass of water with nothing else in it at any point in time, it's going to be a pH of 7, which is neutral, which is perfectly harmless to us. Okay? However, in an acid situation, you have something different. You have, in a solution, an excess of hydrogen ions. Okay? If you have an excess of H+ relative to OHs, you've got an acid. And remember, these ions are highly, highly reactive, and you've got lots of them now. They are eager to bind to other molecules, and in a living thing, the molecules in your body, if there's a bunch of hydrogen ions trying to bind with them and so on, they will succeed and begin to change the chemical structure of the molecules making up your own body. And that, of course, can be devastating. You're altering the shape of molecules by pulling molecules apart so that these hydrogen ions can interact with them. And please remember, in biology, shape matters. It is everything. The shapes of molecules matter and how they do their jobs. And if you submerge a molecule in a bunch of hydrogen ions in a low pH solution, they will begin to disintegrate very often because the hydrogen ions are trying to interact with them. Okay? Same goes for a base. This slide is essentially a repeat of the last one, except for this sentence. Just a different ion. There is an excess of hydroxide ions in the case of a base. For example, if you have a glass of pure water and you pour in a bunch of sodium hydroxide, a basic substance, it disassociates and you have a bunch of extra OH minuses in that water, making it very basic. It's more OHs relative to the H pluses that are in there. So again, they're highly reactive. It really doesn't matter if you're talking acid or base. If you've got a lot of H's or OHs, you have a highly reactive substance there. And it will, either way, you will severely disrupt the structure of molecules. The fewer H's and OH's you have, the closer you are to that pH of 7, which is neutral. Okay, remember, we don't want to disrupt the shape of our body's molecules. Now let's talk about a more specific example in human blood. pH of human blood is right around 7.4, just a bit above neutral. It's very, very slightly basic, and varying even a little bit in either direction. You can see on the screen from 7.0 to 7.8 can be catastrophic, very, very damaging to the molecules in your body. So let's say you drink a nice icy cold can of Coca-Cola, one of my very favorite things to drink, okay? And that I believe said had a pH of 3 on average. Colas have a pH of 3. It's pretty acidic. So how does your body deal with that? I clicked a little too fast. Your body deals with that by, fortunately, having buffers within it to deal with that. In your bloodstream is a lot of CO2. Okay? Why? Well, as we'll learn exactly why later in the year, but right now everybody knows you breathe in oxygen, and when you exhale carbon dioxide. Your body is taking that oxygen, using it, and spitting out CO2 as a waste product. Okay? And that CO2 has to go from the cells in your body through your bloodstream to your lungs to get exhaled. Well, while it is in your blood, that CO2 combines with the water that is also in your blood. The blood plasma is largely water that your blood cells are floating around in. And it forms carbonic acid, which is a very weak, which is a weak acid. Now, weak acids are excellent buffers, okay? Now, here's why. Okay, your weak acid over is shown on the left side of the screen. This H2CO3 is carbonic acid. If you have a rise in pH, it goes up from 7, which means it becomes more basic, more OH negatives. Let's say for somehow you got increased base in your bloodstream. Okay, carbonic acid will break apart and donate hydrogen ions. It will break apart. It will become bicarbonate, HCO3- and extra hydrogen ions to try to balance out those OHs, okay? And bring your blood back down to neutral pH. On the other hand, let's say you drank that Coca-Cola and now your pH is dropping because you're getting more hydrogen ions because you've taken this acid into your body. This bicarbonate that is, again, floating around in your body as part of this carbonic acid will accept hydrogen ions and take them up and again isolate them and prevent your pH from dropping so much. It'll keep it at that neutral 7.4 level. So again, what's the point of all this? Buffers in your blood Weak acids, usually like carbonic acid, allow your body to, again, maintain homeostasis, this time with regard to pH, where we're going to prevent a wild fluctuation. We're going to keep it steady. If the pH gets too high, the carbonic acid will donate hydrogen ions into the blood to neutralize that pH. If the pH gets too low, that carbonic acid, or the bicarbonate more like properly stated, will absorb the hydrogen ions. And so, all thanks to carbonic acid and its alternate bicarbonate, your pH will remain very, very close to where it should be. So, one more question that I ask, because students sort of get messed up here. Is water a good buffer? No. Okay? And the answer as to why is because, well, again, a buffer has to be able to absorb a lot of hydrogens or give off a lot of hydrogens, and water is not good at that. I said, very rarely does water dissociate. Okay, every now and then an H plus and an OH minus fall apart, and then they come back together. It is not a good buffer. Think about it. If you have a glass of water and you start dropping hydrochloric acid into it, that pH is going to plummet. Water has no buffering capacity, so water is a lousy buffer. It's great at many, many things, a very wonderful substance, but being a buffer is not one of the things that water is good at. Carbonic acid is a good buffer. Luckily for us, our blood has it. Okay? So, summary, homeostasis. Okay? That is something you should be aware of from at least first year biology. It is the levels of organization in living systems. The most fundamental living thing you can have is a cell. Every cell, every tissue, many cells working together to do a common job. Every organ, bunch of different tissues working together to do a common job. Every organ system, bunch of different organs working together to do a common job. For example, your digestive system, your stomach, your esophagus, your intestines working together to get nutrients to your body, whatever. Okay? And every individual organism, okay, at the point of life for all of these different levels of organization is to maintain homeostasis, okay, so that the molecules have the right conditions they need to do the things they need to do. The minute the individual, the organ system, the organ, whatever, the cell is unable to maintain homeostasis anymore, it begins to break down. Okay, so maintenance of homeostasis is very important. And again, that's another common thread that we will talk about as we go through our year. So when in doubt, you might want to just raise your hand and say, because it helps the organism maintain homeostasis, and very often you will be right if I ask you why something does something. So I hope you are doing well, and that's it for tonight, and we will talk again soon. Thanks for watching.